All right, let's talk about exponential growth. Now, when we use exponential growth, we use this model, and r is going to be some positive number. It's important, though, that we keep in mind this is just a model of growth, and it's a very good model to use, but we need to understand its limitations, and we'll talk more about that later. The main thing I wanted to say is from here is that this assumes that growth can be continue without limit. So what we're doing is we're using an equation, or a function rather, that grows to infinity. And that's not, you know, always going to be possible in the real world. I guess it's almost never going to be possible. But anyway, it's still a good model as long as we don't go out too far with our t. So let's look at this example. At noon, there are 80 cells in a culture in a petri dish, and the population is growing exponentially. At 1:30, there are 104 cells, and it continues to grow at this rate. How many cells will there be in the culture at 4 o'clock? Okay, well, like before, we've got to solve for r. We've got to solve for r first, and then we can figure out how much is going to be in there at 4 o'clock. So let's see. At noon, 80 cells. So that's how much we start with. And at 1:30, there are 104 cells. We've got to solve for r. Now, what do we use for t here? There are two possibilities. This is an hour and a half, so I could use t as 1.5. The other thing I could do is I could use t as 90 minutes. And either way is fine as long as we keep that in mind, and then you know, in answering any questions, keep in mind that this is going to do things in terms of hours. Okay, so let's find r. So 104 is 80 times e to the 1.5 r. So 104 over 80 equals e to the 1.5 r. Take the natural log of both sides. 1.5, I'm going to rewrite that as 2/3, or as 3/2. And that way r is going to be 2/3 ln of 104 over 80. And just to throw that in my calculator, let's see, 2/3 times ln of 104 over 80. I realize I could reduce that fraction, but I'm just going to stick it in the calculator. This gives me r is 0.1749, and it keeps going. All right. So that means that our model here is a of t is 80 e to the 0.1749 t. So let's see, we're talking 4 o'clock. 4 o'clock, t is 4. So a of 4 is and again, I'm truncating this to 4 decimal places, but in my calculator, I'm keeping the full thing. So I'm going to do 80 e raised to the answer, because my previous answer was the r value, times 4 gives me 161. It actually says 161.04, etc. But this is a number of cells, so they only come in whole numbers, so I'm going to round to the nearest whole number here. All right, let's look at another example. Population of a town in 2014 was 4,200 people, but it grew to 5,100 in 2018. Assuming exponential growth, what's the expected population in 2025? All right, so Um, this is our initial point, 4,200 people in 2014. You know, if you want to, you could even make a chart. Year, T, and population. So in 2014, that's going to be our starting time. So that's going to be T equals 0. Population is 4,200. In 2018, that's 4 years after the start, 5,100 people. And so the population in 2025, let's see, 2025 is 11 years later. And that's what we've got to solve for. So first up, we'll use this. So we'll use these two. A is 5,100. A naught is 4,200. R is what we're solving for. T is, in this case, 4. Divide both sides by 4,200 and round, or not round, reduce. You get 51 over 42 is e to the 4r. So let's see, ln of 51 over 42 divided by 4 gives me a growth rate of 0.0485, and that keeps going. So the question is, when t is 11, a of t here, that looks like an r, it's just a scribble. A of t is going to be 4,200 e to the 0.0485 times 11. So let's see, 4,200 times e to the answer times 11 gives me 7,163. 0.6, we'll round that up to 7,164 peoples. And that's it. All right. Now, this example and the Petri dish example, they're both good problems, and both of them are realistic problems. This is a good model for figuring out what the population will be in 2025, but it probably wouldn't make sense to use the same model to figure out the population in the year 3000. Why? A lot of stuff is going to change in that amount of time, and the model probably won't be valid anymore, or at least for that far into the future. Same thing for this Petri dish. This is good for figuring out how much bacteria there's going to be at 4 o'clock, and it'd probably still be pretty good for maybe the next few days. But you couldn't say, you wouldn't want to use this to say how much bacteria will be in the thing, say, in 10 years. Why? Because the culture is going to grow, and it's going to start overcrowding, and they're going to run out of food, and all these dreadful sounding things. And the model is going to break down. So what we're going to look at for the last part of this is growth with an upper limit. And I'm going to save that for the next video.